All right, so we're going to move on to the next quantum problem, which is called the infinite square well. This is probably one of the most famous Schrodinger's equation problems you will find. It's a very interesting problem, and it begins to show how we use Schrodinger's equation for more and more complicated systems. So if you remember, the whole point of Schrodinger's equation is it's a differential equation that allows us to solve for the wave function of a system. That is, that thing which has built into it all the information one can possibly know about a system. And what's interesting about this particular equation is that it's a single equation that actually stands for an infinite number of equations. Because if you look at it, minus h bar squared over 2m, second derivative of psi with respect to x, plus v times psi equals e times psi. This is, of course, the time-independent Schrodinger equation. This equation stands for every single equation that we can think of because this v can change. The potential is the thing which describes what makes one system different from another system. So previously we did the free particle, which is a particle just going along in empty space, nothing interacting with it. So obviously that's the most simplistic thing. However, once we start allowing some interactions with the particle, we get more and more complicated systems, and so the potential describes what these interactions are. This, what I'm about to show, is the next most complicated thing, the simplest being free particle. This is second simplest, or the next most complicated. And it's called the infinite square well. And the way it works is this. Say you have a particle in a box. Okay, so here's your box. A particle's in here, and it's allowed to move anywhere in this box. And the thing is, this box has walls that are infinitely high. Okay, so you have a box, the box is infinitely tall, you put an object in this box, there's no way that object's going to get out, right? Because in order for something to get out, you have to lift it over the wall to take it out. Well, if the wall itself is infinitely high, there's no way you could ever lift it high enough to get over the wall. That's the point of this particular problem. We are restricting the particle to be in a certain region, and we're disallowing it from being anywhere else. And so the way we do this mathematically is, of course, we draw it as a mathematical function where all of this over here, this is all wall. The wall extends infinitely far in both directions. So all of this is wall, and the walls go up infinitely high. And the walls are located between point 0 and point A. So this is x and this is v. Okay? This is a visual image of our particular system. There's a free space in the region of x goes 0 to A, but outside of that region, you have infinitely high walls that this particle cannot get through. How do we write this mathematically? We do what's called piecewise notation. Piecewise. So we write it in pieces. Our potential V, as a function of x, is equal to, well, between 0 and A, 0 less than x less than a, in this region, the potential is 0. That is, the walls are at 0 height. There's nothing there. However, on the left side, everything before a, so x is, 0, everything before is 0. So x is less than, x is less than 0, all the stuff on the left. The wall that's sitting there is infinitely high, so it's got a potential of infinity. And then everything to the right of a, so x bigger than a, again, the wall is infinitely high. And now we have the mathematical form of our potential. It's broken up into pieces, so we call it piecewise notation. And our potential is between negative infinity all the way up to 0, so all the stuff on the left, the wall is infinitely high, so v is infinity. Then we get to 0, and everywhere between 0 and a, we don't have a wall. You're just empty space in there, nothing's there. So between 0 and a, our potential is 0, nothing. And then once you get to a, everything to the right of a, x is greater than a, the wall is again shot up to infinitely high. So our potential is infinity there. So that's how we write our v. So now what we're going to do is we're going to solve Schrodinger's equation for this v being placed right there. And we want to see how to do this. So let's look. What does Schrodinger's equation look like? I'll rewrite it. H squared over 2m, second derivative of psi with respect to x, plus v as a function of x psi equals e psi. And we want to place our piecewise function. V is infinity for negative infinity less than x less than 0. So this is between 0 and negative infinity, all the left stuff. It's 0 in the region between 0 and a. And it's again infinity for x greater than a. Okay? How do I do this? What I do is there's 3 pieces of my v, so I'm going to have the Schrodinger's equation 3 times. So here's the first, minus h bar squared over 2m, second derivative of psi with respect to x squared, plus, what is v for the first section? V is infinity. So infinity times psi equals e times psi. Well, here's a problem. There's an infinity in this equation. You cannot have an infinity in this equation. So this implies there is no psi. Does not exist. So what does this tell me? This tells me, when I look at the picture, on the left side, from 0 all the way over to the left, if I have no psi, if I have no wave function, that means the particle does not exist anywhere over there. What about number 2? Let's look at the second section. Minus h bar squared over 2m, second derivative of psi with respect to x squared. And then we have plus v times psi. What's v in the second section? It's 0 now. So v is 0. So 0 times psi is just 0. And we have equals e times psi. There's our equation. Now if you look, and you remember from last time, this is exactly what the free particle was for that problem. The free particle equation became this exact thing. So, of course, we can go on and solve for psi, but for now, we'll leave it to solve later. We have it set up. That's all I cared about. What about the third section? Third section, again, minus h bar squared over 2m, second derivative of psi with respect to x squared, plus v psi. What's v in the third section? There it is. It's infinity. So again, we have infinity times psi equals e times psi. Again, we have an infinity in our equation. This is bad. So we get psi does not exist in this region. So we have three regions. X less than 0, 0 less than x less than a, and x greater than a. Those are our three regions. First region, psi doesn't exist, so we don't even worry about it. Third region, psi doesn't exist, we don't worry about it. Now, all we have left is number 2. So we do it. We say, okay, for region 2, we have, which is, let me go ahead and write the region. It's the region that's between 0 and a. Okay. What is our equation? Minus h bar squared over 2m. Second derivative of psi with respect to x squared equals e times psi. And again, I want to solve this for psi. So let me rewrite it. Second derivative of psi with respect to x squared equals minus 2me over h bar squared times psi. So I took this term and I brought it over there. Next, I'm going to take this stuff right here, and I'm going to call that thing k squared. So now I have second derivative of psi with respect to x squared equals minus k squared psi. And now the math comes into play. I need to solve what function psi gives an answer to this differential equation. I take two derivatives of the function, I get back the function again with a negative sign and some constant out in front. Well, we did this last time. We already know what the answer is. The answer, psi, must be some amount, some number, sine kx, plus some other amount, cosine kx. There's our function. Now, we're not done. At this point, we're going to diverge from what we did last time with the free particle, because now we're restricted. Remember what our region is. This wave function is only true for the region 0 to a. So that means there's some boundaries involved here. This isn't true for everywhere. This is only true for a certain point. So we say boundary conditions. We need to find what's called, or use what's called boundary conditions to try to figure more things out. So let's look at boundary conditions. Boundary conditions, if you remember differential equations, are things like the function is equal to 0 when x is equal to 0. So something like y at 0 equals 0 and y prime at 0 equals 0. Things like this. Or y at a is equal to 0. Things like this, these were called boundary conditions. And what they did for differential equations is they say, you may have a general solution to the equation, but to make a specific solution, one for your specific problem, we need to know a little bit of extra information. What information do we need to know? These things tell us. Something like, at the point x is equal to 0, what is the value of the function y? In this case, it's equal to 0. So I feed that information into my solution, and it tells me something. It gives me a better answer than I had before. So we need to know, what are the boundary conditions for our problem? It turns out that for the infinite square well, the boundary conditions, there's two. We have psi at x is equal to the first boundary, x is equal to 0, must be 0. So there's our first boundary condition. Okay, how do we use the boundary condition? Well, what we do is we look at our solution, which is what's here. So we write it. Y is equal, oh, not y, I'm sorry. Psi is equal to a sine kx plus b cosine kx. And we say, all right, when x is equal to 0, psi must be 0. So, okay, psi will be 0 when everywhere I see an x, I'm going to call the x 0. There we go. So all I did was rewrite this equation. Everywhere I see an x, I plugged in 0. And everywhere I see a psi, I plug in 0. Okay, fine. Now let's investigate what this says. First of all, k times 0 is the same as 0. K times 0 is the same as 0. Okay. So what is cosine of 0? Cosine of 0, that's just 1. What about sine of 0? What's the sine of 0? 0. So this equation says 0 equals a times 0 plus b times 1, which is just b. Right? A times 0 is 0. B times 1 is b. So b is equal to 0. Right? 0 equals b. I just figured something out. Right here. B in our solution is always 0. So now we have a new solution. More specific to our problem. And it says psi is a sine kx. B is 0, so 0 times cosine is just 0. So here we go. There's our new solution. However, we have a second boundary condition. We're not done. Notice we still have an a sitting there. We still have a k. These things we don't know. Our second boundary condition says psi at the other boundary. So first we did the left side boundary over here at 0. Now we're doing the right side boundary, which is over here at a. So psi at x is equal to a must also be 0. All right, well, let's just plug it in. We have psi is equal to a sine kx. And again, now everywhere I see an x, I'm going to plug in an a. Everywhere I see a psi, I'm going to plug in a 0. So we have 0 equals a sine k times a. Let's go to the next page with this. 0 equals a sine of k times a. Okay, when is this true? When does a times sine ka always equal 0? Well, we could say a, capital A, is equal to 0, right? If a is equal to 0, then this whole thing is 0. But that's dumb, because if we make capital A equal to 0, and b was already 0, then our psi, our wave function, is just 0. There's nothing there. So we're not going to allow a to be 0 here. Well, if this is not 0, then this thing has to be 0. So now we have to ask ourselves, when is sine of k times a equal to 0? Well, remember what a is. A, this little a, that's just a number. That's like 2, the 4 meter mark or the 3 meter mark. It's where are the walls for this box. So a is just a number, little a. So, when is sine of something equal to 0? Sine of something is equal to 0 when this something is equal to 0, or is equal to pi, or it's equal to 2 pi, or 3 pi, and so on, right? Sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0. So what I need is k times a is equal to some number times pi. This n can be 0, 1, 2, whatever number it wants, any integer number. So when the thing inside the sine function, k times a, is any number times pi, then sine will always be 0. And we've figured out our boundary condition. Well, now let's look at what we have here. This is fancy. We have k times a equals n pi. But what is k? If you remember what k was, let's look back. K was given right here. K is square root of 2me over h bar squared. That's k times a is a number equals some n times pi, where n is an integer. Well, what do I want to do with this? Why am I writing this? First of all, don't be worried if you're wondering why in the heck I'm doing what I'm doing. How do I know to do any of this stuff? You're not supposed to know to do this yet. People worked on this for decades and decades. They didn't just know, oh, we should do this. They played around with a whole bunch of stuff until one of the things they tried gave some good information. So just accept where we're going, but don't worry whether you would have found your way down this path or not. It doesn't matter. I'm trying to lead you down the path, and now you know, this is what we should do. I guarantee you, when I first learned quantum mechanics, I did not know that this is what I should have done. The teacher told me, this is what people did in the past, and this is what happened, and so now we always do it. Well, I'm going to tell you, the reason I'm writing this is because what I want is this little thing right here. E. That's the energy. If I take this equation and solve for energy, then I have a formula for what are the allowed energy levels for our particle. This is the heart of quantum mechanics. What this is about to tell us is that you cannot let a particle that's in this box have any energy in the world. You'd think this is the way it works, right? If you have an actual baseball or a basketball, well, you could give it any energy, right? You could make it any gravitational potential energy. You just lift it to any height. Or you could give it a kinetic energy, just throw it faster and faster. And no matter what energy you want to give it, you just give it that much more speed. There's no limit. There's no unallowed energies. You can just change its height or change its speed and you get to the new energy. But what we're about to see here is that that's not true on a quantum mechanical level. We're about to get an equation for energy that allows only specific numbers to be true. So let's do it. Let's take this equation and solve for E. Well, what I'm going to do is I see a square root sitting there. I don't like that, so I'm going to take the square of everything. So that becomes 2 times m times e over h bar squared. The square root canceled out. And now I have a squared, because the a got squared, equals n squared and pi squared. I just squared everything. And now I want to get e by itself and bring everything else to the right side. So now I have e equals n squared, pi squared, h bar squared, over 2 times m times a squared. And now we see our energy formula. A is a number, so that could be any number. It just depends how big our walls are. M, that's the mass of the particle we have, so that could be anything. H bar squared, that's just a number. It's a constant. Pi, constant. N, however, cannot be any number. N is specifically integers. That's what we picked over here. It can only be 0 or 1 or 2. It cannot be 1.5 or 2.17. It has to be either 1 or 2. So that means all the numbers that would exist for energy, where n has to be between 1 and 2, cannot happen. Thus, it's what's called quantized. It could have one energy level, so let's say this is the energy. It could have this energy level, or this one, but it cannot be anywhere in between. N could be 1, 2, 3, and so on, but you can't have anything in between them. So now we're seeing what quantum mechanics is all about. The fact that you stuck a particle into a box, for some reason, on a quantum mechanical level, limits the allowed energy. For the free particle we did last time, that wasn't true. Free particle can have any energy. But now we're restricted. The fact that the particle must be in this box and can't be outside says it's got quantized energy levels and it can't have anything in the world it wanted. Let's continue though, we're not done. That is important, so I'll star it. But we're not done. What do we have? With our boundary conditions, we found that the wave function is a sine kx with an energy n squared pi squared h bar squared over 2ma squared. Okay? But notice, we still don't know what this A is, this capital A. That's still a random number that we haven't figured out. If I can figure out what that number is, I now have all the information perfect for our wave function. So there's one more thing that's like a boundary condition we need to know. And this thing is called normalization. It's one more step we're going to have to do. What is normalization? It stems from what does the wave function represent. I said a long time ago that the wave function has all the information about the system built into it. But I also said the second thing it represents is the probability of finding the particle somewhere. And in fact, it's not the probability, it's the probability density. The probability is the square. So if you take psi and you square it, technically it's a fancy psi star times psi. But you multiply psi times psi, you square it, but in terms of complex numbers squaring, that's the probability of finding the particle. So, if that is true, then it must mean, if we take what's called the integral, from negative infinity to infinity of psi star psi dx. What is this? This is square psi, that's that part. The integration means take that function and look between this value and that value for x. So if I take the probability of finding the particle and I'm looking between this point and that point, everywhere in between, What does that mean? I'm looking everywhere. All the way from negative infinity, all the way on the left, and I keep searching all the way to the right, and everything in between. If I look, and I take the probability of finding the particle, then it must be equal to 100%. It must be 1. Because if the particle exists, then if I look for it everywhere in the universe, I have to find it. Now, if I look, for instance, if I take the integral psi star psi dx and I go from A to B, some smaller region, then this doesn't have to be 1. This could be some number. It could be 0.1 or 0.05, depending on what this region is. If I'm looking at a very small region, then the chances of finding a particle are really low. The bigger the region, the more likely I am to find it. If I look everywhere, which is what this one is, then I have to find it, because it must exist. This is what's called normalization. I set up the probability of finding the particle somewhere in the universe, and I set it to be equal to 1. And what this is going to do is it's going to normalize the function to guarantee that the probabilities add up correctly. If I don't do this, this capital A in my wave function will allow probabilities of 200% or negative 3%, things that don't make sense. So I have to do what's called normalization to ensure the fact that the probabilities will work out correctly. Okay? And all it means is to write this equation and solve it. So that's what I'll do. Normalize. All right. Integral from negative infinity to infinity of psi star psi dx is equal to 1. There's my normalization. And now all I do is I plug in my value of psi into this equation. So, negative infinity to infinity. Psi star, well, if you watched about the complex numbers, you know that psi star means complex conjugate of psi. Complex conjugate of psi means everywhere you see imaginary number I, put a negative on it. Well, if I look at psi, there is no imaginary number I. So I just write down psi. A sine kx. So there's psi star. And now I need psi, which is the same in this case. Dx is equal to 1. There's my equation. Let me multiply everything. Integral. A times A is A squared. Sine kx times sine kx is sine squared kx. Dx is equal to 1. Now notice the limits here from negative infinity to infinity for my problem change. And the reason they change is because the region is this region here. The other regions, x less than 0, just get 0 from my wave function. There's nothing there. X greater than a, again, I get 0. There's nothing there. So I only care about the region between 0 and a. So my integral becomes an integral between 0 and a, the region I'm talking about. And now I have my equation. Unfortunately, this is an integral equation. Here's what it looks like. A squared integral 0 to a sine squared kx dx is equal to 1. And now I have to solve this. What am I solving for? I want to know what this capital A is. Well, let's try to do it. A squared stays out in front, and now we have this integral. Integral of sine squared. The way you do this is take the sine squared And remember that sine squared kx is the same as 1/2 minus cosine of 2kx over 2. So now what we have is integral from 0 to a of 1/2 dx minus integral 1/2 cosine 2kx dx. And all this is equal to 1. All right, so a squared times. Well, integral of 1/2, that's just 1/2 of x. So it's x over 2 evaluated from 0 to a. And this next integral of cosine 2kx is 1 over 2k sine 2kx. And this is evaluated from 0 to a equal to 1. Now let's look at these two pieces. Let's look at this piece over here. When you evaluate that part, you get a over 2 minus 0. Or 0 over 2 is the same as 0. So you get a over 2. Nice. What about the next part? Let's look at this. We have 1 over 4k sine of 2ka. So we get 1 over 4k sine 2ka minus 1 over 4k sine of 0. Well, that's just 0, so we don't worry about that. So what we have is a squared times, let's look at what we had. The first part is little a over 2 minus the second part is this here, 1 over 4k sine of 2ka. However, what was k? Notice we did something earlier where we figured out something about k. K we found right here. K is n pi over a. So everywhere we see a k, let's put k equals n pi over a. So we have a squared times a over 2 minus 1 over 4n pi over a sine of 2n pi over a times a. A cancels a. Sine of 2n pi, that's just 0. So this whole term drops out, and we're left with a squared times a over 2, all equal to 1. And now we got it. Solve for a. A then must be square root of 2 over a. Now what I should have done, to be honest, is when I wrote down the wave function, I shouldn't have wrote k here. I should have wrote n pi over a instead of k this whole time. But it doesn't matter. We know what it is now. So now that I have this, we now finally have psi, our wave function, is square root of 2 over a sine, instead of kx, it's n pi x over a. Here's our wave function. And our energy levels, n squared pi squared h bar squared over 2ma squared. We now know everything possible about this system. How did we do this? Let's go back to the beginning. We started with Schrodinger's equation here for this potential, which is the infinite square well. This potential has three regions. So we write Schrodinger's equations for each region. Region 1, Region 2, Region 3. Region 1 and 3, the potential is infinity, so the wave function is 0 for those. You can't solve that, so psi is 0. For region 2, however, the potential is 0. We can solve this problem, which is what we did on the next page. So for region 2, this region, we have Schrodinger's equation. We get it into standard form of a differential equation and solve for psi. We got psi to be a sine kx plus b cosine kx. This is a general equation. General equations are not good enough, so we use boundary conditions to get more specific numbers. In this case, for this problem, we have two boundary conditions. Because we have two boundaries. We've got the left wall and the right wall. So the left wall, which is at x is equal to 0, says our wave function must go to 0 at the wall. It can't exist past the wall. So everywhere x is equal to 0, our psi will be 0. We write down the wave function, plugging in 0 for all the x's and 0 for all the psi's. And we follow what this tells us, and it tells us b then has to be 0. Good. So we got one of the two unknowns sitting there, gone. So now we know our wave function must be a sine kx by itself. So we use our second boundary condition. Everywhere there's an x, we plug in a. Everywhere there's a psi, we make it 0. So we plug that stuff in, and what we get is an equation that looks like this. A sine ka is equal to 0. This is only true for k equal to n pi over a. What that does is it gives us an energy. We now know the quantized energy equation. But we also now know what k is. K is n pi over a. Perfect. Now what do we have? The wave function, a sine kx. Now I can rewrite this. K should have been written n pi over a times x. And we know the energy, at least the equation for energy. However, we still don't know that capital A. We still want to know it. So we use our last thing, which is called normalization. And a normalization condition says the integrate over all space, psi star psi, or psi squared, and that should give you 100%, or 1. So I make the condition for our particular wave function, looking only at the region that we're interested in, which is region 2, because the rest we already know is 0. And we do a bunch of this integral. This is where the hardest stuff is going to happen, because integrals are hard. So I will post on Canvas, or I think I have posted actually, a couple of integral tables. These are pages that have integrals already solved for you, so you don't necessarily have to go through the process of solving an integral, because a lot of these are going to be difficult. I don't care about your ability to solve integrals, I care about your ability to work through the problem. So you have on Canvas integral tables, so all you have to do is look, do I have in this integral table something that looks like this? It may not say little k, it may say a or something, doesn't matter. Anyway, give the solution to the integral, write it down as much as possible, set it equal to 1 because it's normalization, and we solve for our final coefficient, capital A. Once that was done, we now have the official wave function and energy equations for the infinite square well. And there we go. This is the second easiest quantum problem, and you can see it took me about 45 minutes to solve this. Now, with practice, obviously we could do this a lot quicker, but I tried to go fairly slow through this step by step, And all I can say is I expect everybody's still somewhat confused. It's not perfectly clear. What you want to do is take a piece of paper, go through this video again, following along, writing out each step, and making sure you understand how each step was done. Work your way through it, see if you can get the answer. If so, do it another time without the video on. Can you, with a blank sheet of paper, solve the infinite square well, do the boundary conditions, and do the normalization? I guarantee you, part of the final exam for this course will be to do exactly that. I'm giving you one of the biggest questions you're going to get. So you need to do this. You need to practice over and over and over again. Now, next time we're going to discuss, now that we have the wave function, how can we ask questions? How can we get information? For instance, I may say, what is the average position of this particle? Where will you find it? So if you remember what the graph looked like, here's the particle is here, there's a big old wall over here, there's a big old wall over here, this is 0, this is A. So if I say, what's the average position? Well, I would expect the average position to be probably in the middle here. So maybe A over 2 is the answer. Certainly I don't expect it to be out here, because there's a wall there. But mathematically, I want to take the wave function psi and take out of it the probability of finding the particle here or there, or if I go to look, which location has the highest chances of being found? Or what about the momentum? I know its energy, so I know its kinetic energy, let's say. I know how fast it could be moving. So what's the average momentum of the particle as it's in there? How do I ask, and thus how do I answer those questions? That's what we're going to do next time, and that's called expectation values. And what we're going to find is you take the psi that we just found, and we put it in an integral, something like this. So we say, what's the most likely position, x, to find a particle if we're looking between the regions, or, let's say between the region 0 to A. What's its most likely position? Or we can ask, what's its probability of finding things like this? This is what we're going to do next time. Before you're able to do it, you have to be able, on your own, with a blank sheet of paper, go through Schrodinger's equation for the infinite square well, do the boundary conditions, do the normalization. If you can do it, you'll be great. You'll definitely get most of the final exam right, and we can move on to the next topic. So please go through this. If you have to, go online, go to YouTube or Google infinite square well, and see how other people talk about it, see how they go through it. They may go through it a little quicker, or sometimes you might see their definition of the infinite square well is the walls go, they're at negative A over 2 and A over 2. So you have walls like this instead of between 0 and A. It's the same problem, you just shift where the walls are. So don't let that confuse you. The process is what you need to know. How do you set up the differential equations? How do you solve them? How do you set up the boundary conditions? How do you solve those? And how do you set up the normalization condition? So, I wish you luck, and I'll see you next time.